Thanks. Hi, I'm Joseph, and I'm CTO of QAware. We're a custom software development company based in Germany. To be more precise, based in Bavaria. That's where beer, Oktoberfest, and FC Bayern comes from. Yeah? But today I don't want to talk about this. We also love Spark, and I want to share some experiences with you on building a Clickstream analysis solution for one of our customers, and it's based on Apache Spark. But first of all, what was the challenge we were faced? And the challenge was our customer wanted a Kettle to rule them all in the web. Yeah? One big kettle of data. And what is floating into this kettle? It's obviously web tracking data, like clicks or views or conversion events. These are mainly events, a stream of events. The second thing floating into our kettle is ad tracking event data. This is mostly ad impressions, ad impression events, but also ad costs. And ad costs and different cost models like pay-per-view, pay-per-click, or rev share or so. But that's not all. Not only those kinds of events, these are like observations are floating into our kettle. Also, master data is very useful if you want to rule them all. And especially ERP, enterprise resource planning data, like the products you sell on your e-commerce site, or if the product is on stock and what are the margins. To realize use cases like please don't promote or place ads for products you haven't on stock, or cut the costs in ads if the ad costs exceed your margin or so. And the fourth one is CRM data. You want to identify your customer when there is web tracking and ad tracking data floating in. There are different kinds of technologies like cookies, or even we used mouse movement patterns to identify a customer. And then you can get the records of a customer. It's his address or socio-demographic properties like gender or his income. And also from the CRM you can get order data of a customer or returns of a customer, and if performed, some ratings on his creditworthiness. Yeah? So you can realize use cases. Don't put expensive ad for a customer who is not credible. Yeah, that's a kettle to rule them all, but this is only a lot of big bunch of data, and not really the mechanism to rule them all. So what can we do to take actions on this data and to make money out of this data? And the first step is to be clear what your goals are. And there is a magic triangle of e-commerce we use there. It's about retention, monetization, and reach. To be aware on which part of this triangle you want to get into. If you want to get more reach, you place ads and big ad campaigns, no matter what they cost. You just want to get reach, and no matter of the monetization. And monetization, it's another kind. So you have to be clear about your goals, and then you can take actions. And to steer your campaigns, you can launch new ad campaigns, you can modify existing ones, put more money into existing ones, you can place special offers, or you can modify your content structure. Put the more interesting contents on the homepage and so. That are the actions you can take. And the web is fast. It's not suitable if you take these steering actions each and every day or week or month. You have to react within minutes. So an important requirement was that this solution should be a real-time solution. So what are the concepts behind our solution? So I want to take you back to the 13th of March 2015 when we had our first whiteboard session. And this is the initial state of the whiteboard. Of course, it's empty. So, and I asked the customer to paint or to sketch the solution he wants, and he said, okay, there is, at the very beginning, there was the JSON stream, about 4,000 events per second, web tracking, ad tracking, and so on data. And then magic happens. And the outcome of this magic should be business intelligence analytics with ClickView, R for data science and automation rules, and PIG for reporting and dashboards. My next question was, and what's real time here? And the definition was real time, it's a soft thing, is from here, from inbound JSON stream to the events are aggregated and accessible by those analytics things, should be no more than 15 minutes. So it's a relaxed real-time requirement here in this case. Yeah, also at the first whiteboard session, we kicked out ClickView. We ranted a little bit about it, and then it was Tableau. But no worries here. But what's inside the magic? Yeah, we had to deep dive a little bit into this magic because it's really hard to implement magic. So the key part of the magic here is user journey analysis. What's this about? The inbound stream are web and ad tracking events of different kinds of events like click, views, view time when it's really visible, and conversion events. And this is an infinite stream of events. And the first step, if we want to get towards actionable insights, is to assemble user journeys. To take the events of one identified user, and like a string of pearls ordered by time, you collect the events of one user. And you have, for each and every user, you have your own user journey. And you can analyze this user journeys further on. In our case, to mostly calculating KPIs like unique users, how many user journeys you have collected within a time frame, or conversions, how many conversion events per user were in a given time frame, or ad costs versus conversion rate in a given time frame. These are examples for KPIs. So this is inside the magic, but there should be a little bit more around this. I deep dive into this later. But first of all, I want to take you with me to the journey to big data wonderland. That's how we discovered the architecture. We saw pink ponies, we saw beautiful hipsters, and we also saw software slums. And, but before we went into big data wonderland, we wanted to challenge big data solution and ask ourselves, couldn't be a more classic solution appropriate? We called it Larry and Friends. Yeah, and it can look like you have MQ series here to collect the events, forward it to Informatica to do the aggregations, the ETL process, and finally all the stuff is in an Oracle database in a data warehouse, and you can perform the analytics on that. Yeah, but what are the downsides here? Sorry, Oracle guys. The Oracle DB doesn't run very well for data more than 1 terabyte. Maybe this limit is even a little bit lower. In terms of the ingestion speed, the query time, or if you want to have both on a quite acceptable level, you have to invest a lot of optimization efforts to achieve this. So, sorry, Larry, we need big data, and this is not the big data solution here. So, next step, at the next step, we entered big data wonderland, and for years and years, there was one default answer on how to build big data solutions. Hadoop and friends, of course. Who of you did a project within the last 12 months using Hadoop? Yeah, quite a couple, huh? Cool. Could look like this, yeah, you have Kafka, a storekeeper for that, accepting the events, forwarding the events to HDFS, yeah, put in files there, then periodically a Hadoop batch processor processes the events, aggregates them, calculates the metrics, and put it into a close friend of itself named Hive to perform the analytics. This architecture also has some downsides, like the aggregation takes too long. Even 50 minutes was not achievable here with 4,000 events per second. It's really hard, and yeah, you know, programming plain Hadoop MapReduce is a little bit cumbersome. Can be solved by using pig or cascading, yeah, but it's also a downside in this solution, and Hive is not interactive enough. Our customer wanted to perform data exploration, and you need interactive queries. Hive is getting better and better, but last year, mid of last year, it was not interactive enough for our requirements. So, a little bit too sluggish. Here, our friend. So next tries. Now we're entering the Greek symbols, the Greek symbol architectures. Sounds good. We thought we were on the right track. First of all, the Kappa architecture. It's based on stream processing. You have, again, Kafka, then a stream processor. Here we evaluated Apache Storm, which aggregates the whole data and puts it into an analytics database. We evaluated Presto here. And one more part I'll come into right now. So what are the downsides here? The stream processor, especially Storm, has a cumbersome programming model. As you know, Twitter kicked Storm, and they're implementing a new stream processor right now. And yeah, one case, I think, is that the programming model is a little bit error-prone and cumbersome. And more important downside here is that we have stateful aggregations throughout clickstream analysis. Stateful aggregation, for example, unique anything like unique users, unique visits or so, and conversions. For those aggregations, you have to know the history of events. Yeah? If you want to aggregate one event, it's not enough to count up something. You have to be aware of the history of all former events. So you have to keep a state. Yeah? And so when you do stream processing here, you have to use a separate database with high throughput and fast lookups like Cassandra, which makes the whole process here slower, yeah? And which makes the whole architecture and the logic here for stream processing more complex. And it feels a little bit over-engineered, the whole architecture, because we didn't need a latency from here to here within seconds. We only need latency of 15 minutes. So Kappa architecture, not the perfect fit, but way better than before. So the next step could be a Lambda architecture, where you differentiate between a speed layer and a batch layer. And the speed layer is with Storm. Yeah, you shift the stateful aggregations here to a batch layer based on Hadoop. So you have this separate database. The logic gets less complex here up there, but there are still problems. Yeah? Still this cumbersome programming model. You have redundant logic between both layers. and it's overall complex to develop and to operate. So both Greek symbol architectures are feeling a little bit over-engineered. So what was the final architecture we found? So let's get one step apart and have a look on the functional architecture, the functional building blocks of our solutions. For the solution, along the way, we have a collection building block. It buffers load peaks and ensures message delivery. It accepts messages and ensures their delivery on the upcoming process. Yeah? And the client can fire and forget events. Produces a raw event stream into the ingestion. The ingestion takes raw events and handles them basically, applying a schema on an event, time partitions the events, because the output of the ingestion is time frame events, one time frame and all events within this time frame. Deduplicates the event, sanity checks, performs some basic pre-aggregations, filtering and fraud detections. And one very important concern here is that it should tolerate delayed events, should handle delayed events. Next stage is the data lake. Yeah? Here there are atomic event frames, those event frames with events in it. Yeah? The event frame was, in our solution, was about 1 minute. And it stores one file in a schema for this event frame, and it serves as an internal memory. It keeps all events, or it has to keep all events which are floating into this system. Next stage is the processing, and the processing takes, for a given time frame, the data, the events from the data lake, creates the user journeys, unique user sets, enriched dimensions, enriches master data out of this ESB here, and aggregates the events to KPIs. And last but not least, all the data is inside an analytics warehouse, the representation of truth, and it's modeled according a multidimensional data model. And you can perform interactive queries. Having this functional architecture, now what are the technologies we used? For the collection, of course, Kafka, it's an obvious choice here. And for ingestion, we used Spark Streaming. It has a cool programming model, as you know, even getting better with Spark 2.0. For the event data lake, we used HDFS and Parquet. It's a very simple solution. It has a high compression ratio, which is good for an eternal memory, and a high scan speed due to the column-oriented storage in Parquet. The processing are Spark batch jobs triggered each and every minute. This is also a cool programming model, as you know. It's high performance and brings all those things Spark is well known for. And the analytics warehouse is Spark SQL, working on HDFS and Parquet data. And we used it as it has a good connectivity, is able to perform interactive queries. And yeah, all those platforms can operate on one core. It's a Spark core, and it's so easy to develop and to operate. And also a nice thing is, as we weren't sure if Spark SQL is the final solution, it's also good replaceable by other technologies as it uses the Hive MetaStore. So, what did we learn on our way to this architecture? First of all, know the technology choices you have. Yeah? We built a big data landscape map here for the different components to know the choices, to be able to discuss which is the best one for us. Is there a new on stage we can evaluate, etc., etc. But also, we learned to beware of the beautiful hipster technologies, because you can get into disappointment fast. In Germany, we have a rule of thumb about marrying women, and it's about this. If she fits to you. And if she's better than average, marry her. And don't put her into questions if you see a superficial better one. Yeah. So that's the same. Germany. Yeah. And that's the same here. Yeah. Next thing we discovered is a pattern. We call it Polyglott Analytics. We need different kinds of analytics for our use cases, and we use both data stores, the data lake, and also the analytics warehouse. And there are 3 lanes we have in our solution. The first lane is obvious, it's SQL, yeah, with Spark SQL. We also have a small data mart based on PostgreSQL beside this. There is mostly for reporting and also for a little bit for data exploration. The R lane, mostly for data science and automation rules. And we discovered that it's good also to have something to analyze time series data. Because here we have those event streams in our data warehouse, and it's good to have these streams in representation of a time series to do anomaly detection. There are very good time series-based anomaly detection algorithms, and we used also a time series lane based on Chronix. This is an open source project from QWare. That's one pattern. Next pattern is microanalytics services. There are visualizations of data which should be accessible for a lot of people out there. Yeah? And solution A is to buy a reporting server for a lot of money. We preferred a more lightweight approach, and we call this microanalytics services. We implemented a dashboard based on open source technology, basic custom-made dashboard, which assembles visualizations produced by microservices. And those microservices are using those Polyglott Analytics lanes here. Which one is the best? Huh? And one microservice per visualization. And the microservices are using all those open source rich visualization technologies which are available. Yeah? There are great libraries available out there, and it's easy to implement a new microservice. If a data scientist discovers a new report, a new visualization, which should be accessible to the masses, he implements it as a microservice service within a few hours. It's really easy. And so we have a very flexible solution here. Next thing we discovered is no retention paranoia. In the analytics warehouse, we implemented an aggressive forgetting. We call it aggressive forgetting. At the analytics warehouse, we have a clearly retention policy per aggregation level. Yeah? Aggregation level 15 minutes for 30 days, 1 hour for 4 months or so. And that's a policy there. Yeah? Don't keep it too long in the analytics warehouse. But there is a data lake, and this is the eternal memory. And if you need new data structures here in the analytics warehouse, or data you've forgotten there, you can perform replays or refills into the analytics warehouse. One more best practice is continuous tuning. Tuning is mission critical in big data applications, in my opinion, and tuning without measurements is nearly nonsense. So we've instrumented the whole solution with throughput and latency probes, and created a load generator here with pre-collected events from production, and integrated all this into the continuous integration loop. So we were able to measure with each and every property change if it's getting faster or slower, and with each and every software change. That's continuous tuning. So finally, I have a few numbers for you. of our solution, the overall dev effort for the first release was 250 person days, which was less than expected. The first release had 10 dimensions and 26 KPIs, integrated 7 third-party systems, mainly CRM and ERP data systems. The inbound data volume per day is right now about 80 gigabytes, and new data in the data warehouse is about 2 gigabytes per day. And a little funny fact at the end. What do you think is the total price of the cheapest cluster which is able to handle production load here? You remember 4,000 events per second, processed and aggregated within 15 minutes. What do you think? Pardon? 1K per day. Even less. The whole cluster costs less than $500 forever. Yeah, this is our cloud computing case. Customs didn't allow me to bring it with me. And these are 5 Odroids and running the whole solution. And this is able to process the production load. It's not in production, eh? But we performed some load tests, and this was able to handle this. So that's all right now. So I'm open for questions, and thank you.
Great presentation, thank you.
Thanks.
In your Greek architectures, you mentioned about using Cassandra, and you said you were slowed down when you're using Storm into Cassandra.
Yeah.
Where was the bottleneck?
Cassandra itself. It takes some time to answer queries. It's just, it was not, Cassandra took about 5, 6, 7 seconds to look up the history of events, yeah? And this slowed down the Storm processing.
Okay, so people look at Cassandra primarily for heavy, fast writes and fast reads, and that's not what you expected out of that?
No, we expected this behavior. It only slows it down a little bit. It was not so important, but it slowed it down a little bit. Okay. It could be faster, but it was okay. Cassandra did a good job.
And your end analytics warehouse, that is HDFS?
In this case, in the Kappa architecture.
Oh, the last one. The final functional architecture that you showed.
No, it's Spark SQL.
Spark
SQL based on HDFS and Parquet files.
Okay.
We also evaluated Tachyon, but it was not that robust at this time.
Okay. Thank you.
Yeah, hello. Thank you for the presentation. And in your last Spark streaming solution, so I see you are using HDFS and the Parquet file to store your data. And how can you solve the problem you mentioned before? Maybe an event is arrived late, and you need to look at the history data to get a matrix update. So what's the solution?
For performing updates in the analytics warehouse, what's our solution? Yeah, that's really a tough thing there. What we're doing is for the hourly aggregation level, we're using timestamps. We're just inserting new rows into the database and using a timestamp, and the queries have to order according to the timestamp and pick the most recent one. That's what we're doing at the aggregation level of 1 hour and below. For the other aggregation levels, we just take, we're operating on the file level. Yeah? We're taking the Parquet files, deleting them, and writing a new one.
You had a slide where it put 2 microservices.
Oh, sorry.
So
Yep.
who is the consumer, or Spark SQL is a consumer, or the dashboard is a consumer?
The consumer of those microservices? Yeah, the dashboard. The dashboard. All those microservices are registered at the dashboard, and the dashboard is the consumer. And the microservices are consuming data from the data warehouse. And so.
Yeah. Thank you for the presentation. And for the connecting, like you're trying to connect JDBC or DBC to a Spark SQL, why you didn't use Impala?
It's on our landscape. We use Spark SQL because of the uniform operation model, because we have Spark for processing, for ingestion, and so it was, it was the first choice, and it was okay. Yeah, we connected Tableau to Spark SQL, and it performed well, and so we didn't see the need to evaluate another database. But Impala is also a great choice, and all those, you see this new SQL databases, there are a lot of emerging right now.
All right, that's about all the time we have for questions. So if you have more questions, you can talk to Joseph offline.
Yeah.
So let's give him another round of applause.